All right, you guys. We are going to be talking about bond polarity. All right, and we're also then going to change that into what does it look like for a molecule. Okay, so when we are talking about covalent compounds, they are sharing electrons, but they don't always have to be equal sharing. All right, just like with your siblings, I'm sure you always haven't had everything equal. um, Maybe one person got more, maybe somebody got to use something more. You thought, oh, this is unfair. All right. Well, with these molecules, um, they don't necessarily have to have those equal sharing of electrons. All right. So when we are looking at actual bond polarity, all right, um, bonds, if it has something that has polarity, they have what's called electric poles. And that means that one end tends to be a little bit more positive, the other end tends to be a little bit more negative. And remember, positive and negatives with um, atoms here or any kind in chemistry, that's talking about the electrons go towards more one end um, than the other. Okay, so that comes from the polarity would come from unequal sharing of electrons. Electrons like to be around one atom a little bit more than the other. Okay, so if we have what's called nonpolar covalent bonds, this means that they are being equally shared. Okay, so the electrons are just hanging out here in between them. Okay, if we have what is called polar covalent bonds, that means that the electrons are being unequally shared. Okay, so the electrons tend to want to be a little bit more on that chlorine side because the chlorine has a greater electronegativity. Electronegativity, if you remember, has the ability to attract electrons more. Okay, so that they attract electrons a little bit more than the hydrogen. It's still being shared, but this chlorine end tends to be more negative. The hydrogen tends to be more positive. Okay, and we do have symbols that represent that, and that's kind of what's being shown with this picture. Um, this symbol is saying that, oh, there's a positive end down here. It's a little bit more negative on this end. Okay. Then you also have that third type of bonding, ionic, where they're being completely transferred. Okay, so there's no electrons. Sodium just is like, here, chlorine, take my electron. Okay, so one way how we figure out these each individual specific bonds are by the differences in electronegativity. Okay, so on your periodic table, they tell you all of the electronegativities. Okay, and then also on the bottom, it kind of goes through what does the differences mean? Are they nonpolar? Are they polar? Or are they covalent with the bonds? Okay, so if I have it being 0.5 or less, that is going to be considered a nonpolar covalent. Those electrons are being shared. If it's between 0.5 and 1.7, that's polar covalent. So they're still being shared, but the electrons like to go closer to one end or the other. Okay, if it's greater than 1.7, then that's going to be completely transferring. So those are our ionic bonds. Okay. All right, so with those individual bonds, we can tell if they're polar or nonpolar, but we want to look at actual molecules. Okay, so we ask the questions, does the polarity of individual bonds always create a molecule that is polar? What if they were polar in equal but opposite directions? And what about symmetry? Okay, so if we look at these examples right here that we have, um, H2CO, okay, if we look at the bond between carbon and hydrogen, carbon is um, a little bit more negative. All right, the hydrogens are a little bit less, are going to be a little bit more positive. So the electronegativity, the electrons are going to flow closer to the carbon. But you also have this opposite, or not opposite, you have this oxygen. Okay, oxygen is fairly electronegative. So most of the electrons are going to want to shift towards that oxygen. Okay, so if you look at the element or the molecule, okay, um, if there's one end, okay, so one end that is different Okay, so one terminal atom that is different, okay, it is going to be considered a polar molecule. Okay, so one end that is different, it is going to be automatically that polar molecule. All right, if it is not symmetrical. Okay, now if we look at the other side, with carbon dioxide, yeah, oxygen again is going to attract those electrons a little bit more, both sides. So the carbon, okay, is a little bit more positive. The oxygens are a little bit more negative, okay? But what happens is that since these are both negative, they cancel each other out. Okay, they're equal poles. Right? If one happened to be fluorine, it'd be a different situation. But since oxygen is a little bit more negative, but they're the same on both sides, they're equal but opposite. So there's not going to be that more pole on one side. Okay, so you want to look at, is it symmetrical? That means, are the terminal atoms exactly the same? Okay, if they are, it's going to be a nonpolar. So this is considered nonpolar. Okay, if there is a terminal atom that is different, okay, it is automatically going to be polar. Okay, so I'm going to give you a few hints here to how do I remember this? How do I know? Okay, so here's some rules. Okay, all trigonal pyramidal. Okay, so that means that it has a lone pair. So if we talked about ammonia, so NH3, okay, and bent molecules. All right, so bent is where we have um, our central atom, our terminal atoms, and then two lone pairs around it. Okay, those are always going to be polar because they can't have symmetry. Okay, there's no symmetry with unshared pairs of electrons. Okay, so even if the bonds are nonpolar, that unshared pair of electrons in that middle automatically make them polar. They pull those electrons a little bit closer to them. Okay, so that's automatically, you can tell, oh, they have lone pairs, or it is trigonal pyramidal or bent. You automatically know that. Okay, if it is tetrahedral, trigonal planar, linear, or trigonal bipyramidal. We did not talk about this one very much yesterday. You have to look at, do they all have nonpolar bonds? Okay, or are all the exterior, I'm going to change that to terminal. Okay, are all the terminal atoms the same? Okay, if they are all the same, they're going to be nonpolar. Okay, so there's a couple different things to point out with this, just to remember. Either that they are all nonpolar bonds, or is that key word, or they all those terminal atoms have to be the same. Okay, then it's going to be nonpolar. Okay, anything else you need to see are the individual bonds between carbon and oxygen, between carbon and fluorine, oxygen and fluorine, whatever. Are those individual bonds polar? And are they even an opposite? Are they symmetrical? Do they balance each other out? Okay. So we will go through some examples. When you are looking at your enabler, okay, so the worksheets on pages 11 and 12, okay, so if we look at a couple of examples from that, okay, um, you can tell what their shapes are. You can tell if they're polar or not. Okay, so if you look at C2H2, so it looks like this. Okay, first of all right, around the central atoms here, all right, we can tell what the shape is going to be. All right, there are no lone pairs. There's just these bonding areas here, here, and here. Okay, it goes straight across. This is going to be considered linear in shape. Okay, and you're going to say, is it going to be polar or non-polar? Okay, do we have symmetry here? We have H, we have C, C, H. Is it the same things on both sides? Yeah. Okay, so yeah, the carbons tend to be a little bit more, which the bonds between carbon and hydrogen are considered polar. Okay, carbon is, they're going to attract the electrons. This right here, though, is non-polar too. Okay, do we have, because between the same atoms, they don't have any electronegativity, they're being shared equally. Okay, exactly the same thing on both sides, so it's linear. It has symmetry, so therefore, this is going to be considered a non-polar molecule. Okay. All right. So yeah, if it has symmetry, that's the biggest thing. Okay. If it looks the same on both sides, the poles are going to be the same, so they're going to be equal but opposite. Okay. Awesome. It's not working. Okay. So if you have questions, definitely let me know. And shoot me an email, and you can help me out. I can help you out that way, or ask me tomorrow in class. Okay? Have a wonderful day. We'll talk to you later.